So question number 7 on page 113 says, a spring of constant of K of 200 newtons per meter is slowly extended from an extension of 3 centimeters to 5. How much work is done by the extending force? So let's kind of draw our scenario. And what I like to do when I'm talking about springs is like, okay, this is our, equilibrium position where X is 0. So then we had it extended a little bit further, and I'm going to draw just a vertical line there. And then we had it extended even further. So in this case, X is 0.03 meters. And we want to convert everything into meters, no centimeters, and 0.05. Now, to do this, we had to pull with some force of a spring. And that's using Hooke's law of the idea that force of a spring is equal to Kx. And so what we see is that as we stretch that spring farther and farther, that force is going to be greater. So this is going to be the greatest, the second, and then well, this is actually, there is no force here because X is 0. So that's the force of my spring. And so really 2 ways we could go about doing this, and it's kind of interesting to do both ways, is let's first find the average force from 0.03 to 0.05. And so if we do that, the force at 0.03 is going to equal negative Kx, or excuse me, just K. Don't worry about the negative. Negative just deals with direction. So that's just going to be 200 times 0.03, and that's going to give me a force of 6. The force at 0.05 then would be 200 times 0.05, which is going to be 10. And so what I know is Hooke's law gives me an equation of F and X, and it has a line that looks like this, where my slope is my K value. And so we can say, well, what's the average force that's applied? And so the force increases linearly based on the displacement, with my slope being my K value. And so my average force for this then would be, it's kind of like when we find the average velocity, right? It's my initial force plus my final force divided by 2, right? And so that's 6 plus 10 divided by 2, that's 16. And so that's an average force of 8 newtons. And then what I can do is I can find the work done by just do force times displacement cosine theta. My displacement in this case would be in this direction. That's my S. So that's a theta of 0, which makes this just regular 1. And so then the work done would simply be 8 newtons multiplied by 0.02 meters, or 0.16 Newton meters or joules. Same unit. 1 Newton meter and 1 joule is the same. So that's one way you could do it, in using Hooke's law and finding the force at the beginning, force at the end, and then the average force during that pull, and then just multiplying that by my displacement, and that's how I would find work. The other way you could do it is using the idea of energy, and doing that, here the energy of a spring, the potential energy of a spring is 0, where this has energy potential which is greater than 0, and then this has energy potential which is much bigger than 0, but it's greater than this one, right? And so we can use the idea of work and work's ability to change energy. And so the other way we could do it, the other way we could do it is saying, okay, well, we know that work causes a change in energy. And what I have is this would be the energy final minus energy initial. So again, anytime I have a change, delta, that's final minus initial. And so this would be, you know, the energy of the spring final minus energy of the spring initial. And that would be 1/2 K delta X squared final minus 1/2 K delta X squared initial. And I can factor out my 1/2 Ks because that's the same for each of them. And I can just have delta X final minus delta X initial. And both of those are squared. And when I plug that in, again, I get 1/2 times 200 times 0.05 squared minus 0.03 squared. And then if I plug that in my calculator, I get the same thing. I could get 0.16 joules or Newton meters. Again, those are the same thing. Units of energy and work are interchangeable. So that's really how I could do that one of two ways, right? This first way is using Hooke's law. And this way is using the idea of energy. Both of those can produce the same result of the work done, which is 0.16 joules.